Welcome to this walkthrough of Sneaky on HackTheBox. This is the 7th box in our series of 10 HackTheBox machines exploited without the use of Metasploit. We'll start off by running auto recon, and we'll let that run to its conclusion. You can pause the video here and we'll return when the results are all in. And the results are in, so let's have a look. So it looks like we have both TCP and UDP results this time. It appears we have an Apache 2.4.7 web server running on port 80. And SNMP version 3 running on port 161, UDP 161. So starting with the web server, we can see the static under construction placeholder page. But if we look into our basic GoBuster results, then we can see that there is a redirect for the /dev folder. It's worth noting too that this is such a commonly vulnerable area of websites that both Nmap and Nikto find this directory as a matter of course within their scans. So navigating to the /dev site, we can see that we are in the login page for a members only area. If we have a look at the source code for this site, we can see it's really a very simple form with just two fields, name and pass, being passed to login.php. So trying out a couple of test cases, we can see that they're not found. Admin, likewise not found. So let's have a quick look here to see if we have possibility of a SQL injection. We can try just a simple test string. So this is going to terminate the user input and then give it the option or 1 = 1, that is, or true. Anything or true is considered true. So we'll be passing this SQL query logic response true. And that gets us in. And in doing so, it shows us two usernames, admin and Thrasivoulos. And very importantly, we have a link to my key with the overconfident assertion that no one is ever going to find it. So the my key link is to /dev/ssh key for administrator difficult times, and that page contains an RSA private key. So this site is terrible. It uses a commonly used and commonly vulnerable /dev page. Its login is vulnerable to very basic SQL injection that also gives up the names of all its users, and at the end it gives up a user's RSA private key completely unnecessarily. At most, a public key would be sufficient for logging in via SSH. Giving up the private key opens up all of the RSA encryption and authentication to an attacker. Okay, so now we have this precious RSA key. And we can store that in our loot folder. Just call it, start a file called key, paste our key in, and we're set. And if we want to use it in the future, we are going to need to change the permission. So this is required by SSH, or the key will be rejected. The quickest way to set those permissions is to chmod the file with the 600 setting, so chmod 600 key. Each of the digits is a user level. So first the owner, their permissions, then the group's permissions, and then permissions for everyone else. The 6 in the 600 is the decimal number for the binary permission 110. So that turns on read and write, but not execute. If we look at the file permissions using ls-al, as I've done here, this first dash indicates that it's a file, rather than D for directory. The R and W indicate that the owner can read and write. There are no remaining letters, so the remaining dashes indicate that the other read, write, and execute permissions are turned off, particularly for groups and other users. Now let's have a look at the SNMP results. We saw earlier that from the Nmap scan that the service is SNMP version 3, which is good from a security standpoint, provided that it's used correctly. SNMP v3 incorporates mutual authentication and encryption, which was lacking in previous versions. But in this case, it hasn't helped. Here, the service is running on an open public community, which we can see here as its attempt to log in using the public community string. Probably this is for backwards compatibility with SNMP version 1 clients. So rather than a password secured and encrypted private community, we have this openly accessible public community. And we can see from the results as it's running through SNMP walk, looking at each of the object identifiers for each of the possible services running on this machine, that we have a lot of services running on this machine that we have monitoring abilities on. So we can have a look to see if SSH is among them, because we expect it to be in there, but we haven't seen a port 22 open for it. And we can see that SSH is indeed among them. As I said, it's not being served on any ports that we've scanned so far, and we strongly suspect that SSH should be available because there is an SSH key for administrator difficult times, but perhaps it's being made available over IPv6 instead of the IPv4 ports that we've scanned so far. So we can use SNMP to see if we have an available IPv6 address using the SNMP walk command. So this is going to SNMP walk, treating it like version 1 with the public community on our machine 10.10.10.20. And we're providing it with the object identifier 1.3.6.1.2.4, so on and so on. It's the object identifier in SNMP for IP addresses. We can see we've got quite a few coming back. And the pattern that we'll see again and again is this group of numbers as the object identifier, and then either a 4 or a 16. So indicating either IPv4 or IPv6. And you can get some sense that we're looking at an IPv6 address based on the length of it, rather than the short IPv4 addresses. So these results with ISO.3.6, etc., etc., they indicate an IPv6 address, but this decimal format on the end of the SNMP object identifier is pretty cumbersome. Instead, let's get the results using Enix, which is a IPv6 enumerator for SNMP that's available from Trickster Zero's GitHub repo. And this is the tool here. So we'll run it in Python. It is a Python 2 script. The Enix folder, enix.py. Again, we'll tell it to treat it as SNMP version 1 of the public community at 10.10.10.20. And right away, it gives us at least one IPv6 address to try. Our unique local address, dead beef, 000, etc., etc. So if we move back into our loot folder, we can SSH. We use -I to indicate that we're going to supply a key. We'll log in as the Thrasivoulis user at this address. It's going to prompt us to continue if we want to accept the new fingerprint. This is the first time we're connecting to this machine. And we have a secure shell. So running who am I? We can see that we're logged in as the user Thrasivoulis, which makes sense. And we have access to their home file, home folder. And we can display the user.txt file in their, the flag in their folder. We cannot, however, access the root.txt key in the root folder. That's permission denied. So let's grab our lin-enum script to see how we might elevate our privileges. So I'll move into the payloads area where I keep my lin-enum. And this time we don't need to transfer files over HTTP. We can just secure copy them over our SSH connection. So we'll SCP. We'll still need to provide it with the key, which is now in a different folder, so provide that path. In our loot folder. Next we're going to tell it what file we're going to transfer from the local directory, and we're going to send that to Thrasivoulis at the deadbeef IPv6 address. We need to place that in square brackets because it's an IPv6 address. And then we put a colon, and we'll move that to the temporary directory. So it's going to tell us that we've got an invalid format on our public key because we're not using a public key, we're using a private key, but it still works. And after a few seconds, we can see that we've transferred that file over. If we move to temp, we can see that our lin-enum script is there. So as usual, we'll chmod +x, lin-enum, and run it. And I'll let this run for a couple of minutes. You can pause the video here and come back when your results are back. All right, so we're back. We've got some interesting findings in this pile of information that lin-enum gives us back. We've got quite the list of SUID files, including many that we have at least read and execute rights on, including this unusual one right here, user local bin/chal. All these other ones are fairly recognizable resources. We can see that we should have access to our MySQL history as well. So if we have a look at .mysql history, we can see their interaction with the MySQL database, including, well, that they've set their password here. It's a great password. It's long, it's strong, it's complex. It uses misspellings to defeat dictionary attacks. It would be nearly ideal if it weren't easily bypassed by SQL injection and weren't exposed in plain text in this history file. And if we wanted to, we could even test that. Logging in as the Thrasybulus user. And we're in. And it appears that the basic functionality of the site is only to display the name of the current user, but as we saw before, using our SQL injection, we got it to display all of the users. And who knows how many other sites and services this user is using that password for. In any case, we are more interested in the SUID file, that user local bin chow. The only file in here. And as we can see, it's marked that it's got the set user ID bit, and that's why it's marked in red here, just to bring it to our attention. And we have execute privileges on this file. So we can run it, which causes a segmentation fault. We could provide it some user input. We don't get any response out of that, letters or numbers. We can give it a whole lot of user input for days and days and days. And eventually that will cause a segmentation fault as well. Okay? So we've got the makings of a buffer overflow exploit in this program. Now I did a bit of manual testing since it really wasn't that many A's that we had to give it before it faulted out, before it crashed. It turns out that it will accept 362 A's, so 360 characters and no more. This manual checking procedure, though, could have been very cumbersome had the buffer assigned for this user input been very large. Instead, just providing that were the case, we could run a Python script. We do have Python available to us here to find it to the nearest 100. And we do that using a simple Python script. So this is going to import the system and socket. Oh, it doesn't need socket. Yes, it does. No, it doesn't. So this is going to import the system module and the time module, importing the sleep function, and the OS module. So it's going to start by producing a buffer of 100 A's. And while it's running, it's going to try running the system command user local bin chow, so running the program, and providing our buffer of 100 A's. And then it'll sleep for a second, and then it'll add another 100 A's to the buffer. We'll check it at 100 steps, so to the nearest 100. And we should get a segmentation fault after we reach 400. At which point we can break the program and it'll tell us how many bytes were in that buffer when it crashed. So let's copy that file using SCP again. And we just need to give it our file name because we're in that folder with it. Take just a moment to copy over. And then we can run it. So we get our segmentation fault, we stop the program. There we go. Stop the program, and that happened immediately after we hit 400 bytes, which makes sense since we know that it's actually 363 characters that will cause a crash. Typically we would round our output value here to the nearest kilobyte, but we can round here safely to 400 in this case. So next up we want to create a test pattern using a program that's included with Metasploit. It's not the Metasploit framework itself, so it's still on the table for the OSCP. And this program will identify the EIP. It will help us identify the extended instruction pointer. So the EIP, or the return address, is the point in memory where the user input variable was supposed to end, and where a memory address is stored for the program to know where to go next. That is, where should it return to once it has read the user input variable. So our overflow of the input variable's buffer, its assigned space in memory, that overwrote that return address with A's. So 41414141 in hex. And that's not a valid memory address, hence the segmentation fault. So our pattern creator is in the user share Metasploit framework. Tools, exploit, pattern create .rb. It's a Ruby script. And we need to give it a length of the pattern that we're going to create. In this case, 400 should be sufficient. And this creates for us a non-repeating pattern, 400 characters long, so that will trigger a segmentation fault. The next thing we need to do is look into the memory buffer for this program to see where this is all happening. So we're going to need a debugger as well. And this system has the new debugger, the GDB, and we can run the program in the debugger, like so. And now we can run our pattern in the program within the debugger. So we're supplying our pattern using the run command as the user input for this program. So this is what it's tried to run essentially on the command line. Is user local bin chow, and then provide it with our big long pattern as user input. And we can see that we've suffered a segmentation fault, and we get this information back. This is the content of the EIP. So the address that was supposed to be the return address for our user input is in fact overwritten by 31604130, which if we drop it into CyberChef, from hex, is the pattern sequence 1MA0. So somewhere in here. This might be a very large pattern for a large buffer. So our next job is to find the memory offset for our EIP. We're going to need that to redirect the program to a memory address of our choosing later on, so that it will run the code that we want it to run. And we know that the EIP was overwritten by 1MA0, or in this case 31604130 in its terms. So we can use another program included with Metasploit. in the same folder called pattern offset, another Ruby program. The length is 400. It already knows that that's going to correspond to this 400 character long pattern because that's the same system as it's creating it. And we're going to query against this 316D4130 string. And it tells us that we've got an exact match at offset 362. So that means that 362 characters into our buffer, that's when our EIP starts, because that's where we found our pattern. And that's as we expected. So this is beyond the scope of what we're doing here, but if we were attempting a buffer overflow that didn't result in a convenient segmentation fault, the next question we would have is, can we overwrite the EIP? Now, we obviously can because we're seeing it happen again and again as we crash the program by overwriting the EIP. We could test it by overflowing the buffer with a controlled string in the debugger. Now, in that case, we would need to set our own breakpoint in the program so that we can examine the program's memory content before it gets wiped by the program ending, which again is beyond what we're doing here, but we can see the same sort of results using our segmentation fault. So in GDB, we could run something like run the program with a quick little Python script running the command print 362 A's and then 10 B's just for good measure. Start the program over again, of course. We get our seg fault 424242, which is the hex for the character B. So we've got a bunch of B's in hex. And we can have a look at the memory space around the crash point, which is where our ESP, our extended stack pointer, is left. So this is where the program was looking at memory last. And the command for that, to examine memory, is x/x. We're going to look at the ESP. So this lets us examine memory, the first x, display it in hex, the /x. In this case, we're going to get one double word of hex. So one hex character is half a byte, or a nibble. 4 hex characters is a word, and 8 hex characters is a double word, or D word. If we had said x/10x, we'd be examining 10 double words of hex. And the last part of our command here is $ESP. That tells us where we want it to look, in this case at the extended stack pointer. So we successfully overwrite the EIP with our B's at that memory position. BFFF560. So with that sidetrack out of the way, our next concern is how this machine and program handle hex as input. Are there any characters that it will treat like they're something else, or that will generally muck up our shellcode if we use them? Are there bad characters that we want to exclude from our shellcode? And this time we're stuck with a bit of trial and error. There are some more elegant solutions in general, but when we supply all of the possible characters using another Python script, which would be our starting point, we have a problem. At least one of our characters is being treated like a return character. None of the other characters after it are sent. So we don't even get a segmentation fault to help us examine memory around the crash point. So when we run a program like this, trying to provide all of the possible characters, at some point early on, before we've even reached our buffer overflow, something is acting as a return character. We're not getting any of the rest of the characters, and so we're not overflowing the buffer. So what this does is put together a string of all of the usable characters from hex 00 to hex FF. And I've broken them up here by lines, not just for appearances, but so that we can comment out one line at a time, like so, until our input triggers a seg fault again, and we can have a look in memory to see if any of the characters are modified. First, though, we need to test and retest by removing one line at a time from the string to see if the program will run and cause a seg fault. Then add back half a line at a time and test and retest until our problem return character or characters are identified and removed. We can also start, as I've done here, by removing 0, 0, 0A, and 0D. They are common problem bytes. This will supply our shellcode. It'll pad out 20 A's first, make up a string starting with 20 A's. We're going to need to find the start later on. And then all of our possible characters. And then just to make sure we overflow the buffer and get our segfault, we add 360 B's for good measure. And that string will be sent to the program as user input. It's just going to print our shellcode here. So we would copy our bad characters Python script over to the target, run it as input within GDB, similar to what we've done here. So just running it as a Python script, instead of giving it the -c, we'd simply give it the name /temp/badcharacters.py. I've gone through the tedious trial and error process and eliminated 0, 9 and 2, 0 as bad characters. One or both of those were causing the issue for us. That is, either they were prematurely ending our string, and so the program didn't segfault while they were included, or the program did segfault, and when I looked into the memory space, I could see that they were not the same character that I had sent in. The system or the program had replaced them with another hex byte in memory, which is not going to be good for us if it does that to a byte in our shellcode. Now with that information in hand, we can finally generate our payload to create a reverse shell. And for that, we will use MSF Venom. So we're telling MSF Venom that we want a payload that creates a TCP reverse shell for Linux, that it's going to be connecting back to our host here, 10.10.14.7, on port 9999. For now, we're just going to tell it to output as C. We could put it into C code, we could put it into Python code, it doesn't really matter, we're just going to get bytes out of it. We do need to tell it what characters are potentially bad, so we've told it that 00, 09, 0A, 0D, and 20 are all our bad characters. And we can provide it with the architecture, in this case x86. So it will churn through that, produce a byte encoded shell script for us that meets those requirements. And after a minute or so, we've got our shellcode. And this we can copy into. So this is what we will be putting directly into memory as our user input. So we start with our offset, which we know is 362. We're going to temporarily set our EIP variable to CCCC. That's what we plan to write to the EIP. We're going to need to cause a segmentation fault at least once here. Then we provide it with our exploit code bytecode from MSF Venom. And finally, we put it all together into one string that we'll send as user input to our vulnerable program. So we start with a whole bunch of 90, /x90. That's the hex for no operation, also called NOP. So when the system sees that, it just moves on to the next memory address. So we're going to have a bunch of them in a row, which we call a NOP sled, so that we don't need to be terribly precise with our EIP. Anywhere on the NOP sled, and it will just next, next, next to the beginning of our exploit code, which is what's next in our string. So we have NOPs to fill up the space before our exploit, right? Offset minus the length of the exploit. And then at the end, we have our EIP. For now, it's just a nonsense CCCC placeholder to cause a seg fault. And that's what's going to print out. So we can copy this over to our target machine as well. And then within our debugger, we will run our script. So it's going to run the chow program. It's going to provide as input the output of exploit.py. and we get a seg fault, and we get 43434343, which is our C's, which means our spacing is right on. And now we can have a look in memory. We'll have a look at 200 double words, starting at 100 double words before the ESP, which is quite a bit. And there we go. What we're looking for is all these 90, 90, 90, 90s. This is our NOP sled. So we simply need to pick any address in this section. So for example, we could do BFF80C, and that's what we're going to replace the CCCC with in our script's EIP variable. So if we go back to our exploit script, we're going to replace the CCCC with the little endian version of our chosen address. So currently that's BFFFF80C. So if we break that up, what we're going to be doing is passing these in as bytes in the reverse order that we would normally see them. That's the little endian format. That's simply the way the system needs the EIP to be formatted. So F8, FF, BF. So now, rather than the characters CCCC, we have the hex bytes OC, F8, FF, BF. Everything else stays the same. We'll copy our modified exploit script back over to our system. And this time, we don't need to run it in the debugger. We'll run it in the main program. So as I said, what we have after all of that is the NOPs, right? The X90, the NOP or no operation, or go to next command. And then we have the MSF Venom shellcode. All of that gets written into the buffer space of our user input variable. And the EIP that we've provided gets, or the EIP gets overwritten with the address that we've provided. That's an address somewhere in the NOP sled. So when the program finishes writing our user input to the buffer, it reads the EIP as its return address. It goes to BFFF80C in the NOP sled, proceeds along the NOP sled until it reaches the shellcode, and then executes our shellcode. So we just need to have a listener ready to catch the connection. And we can run our updated exploit in the chow program itself. And right away we get a connection. And we can see that we're running as root, and that we can cat the root.txt file. So to sum up, this system has a SQL injection vulnerability on the login page of its poorly named developer area. We could fix that with parameterized queries or a secure authentication AP. Those would both be of benefit here, as well as a less obvious page name. Once inside, we were handed access to usernames and an RSA private key, and that's about as bad as it can get, as we've discussed already. For now, though, it gets us in via SSH through an IPv6 address, which we found because SNMP, despite possibly being version 3 on this machine and full of security bells and whistles, was actually operating on an open public community like an unsecure version 1 service. Inside that machine, in addition to finding the user's plaintext password, we found we had execute permissions on a program that runs as root thanks to the SUID bit being set. The root cause of the program's buffer overflow is its use of the command strcopy. We can see this if we open the program in the debugger and issue the command to disassemble main. This will disassemble the main function and show us the commands that are running in the program. And here we can see that strcpy, strcopy, is being used, and that's the problem. The program appears to just take our input and strcopy it to a memory location, and we're giving it more data than is allocated for that memory location. The solution to this is to replace the use of strcopy with strncopy, which will only copy the number of bytes allocated to the buffer. If the code had used strncopy, then everything up to and including our 302nd byte would have been placed in that memory location as planned, and everything beyond that, including our all-important EIP reference, our return pointer, pointing back to the NOP sled and our exploit code, would have been discarded. Sure, the exploit code would be there, but without a way to redirect the program to it, it might just as well be a long string of A's or B's or 5's for all the good it would do us as an attacker. The program itself did very little other than accept some user input and crash when we gave it too much user input, but that left it open for a buffer overflow, which we exploited to gain a reverse shell, also running as root, because all of the processes spawned by that program run as the same user that the program runs as. And the SUID bit makes that program run as its owner, in this case, the root user.